Well, thanks for having me on to speak today, Michael.
Yeah.
Yeah, I'm Mark, and I'm going to be speaking about generative AI for medical imaging in MONAI. Um, so, in the last decade, we've seen huge breakthroughs in machine learning, especially in deep learning, and there have been three main factors which have influenced this progress. So the first is new models and algorithms which have driven forward development. The second is new and better hardware accelerators. So we've got accelerators which are both faster and have more memory available, which allows to train on bigger batch sizes and train larger models. But just as important as these other two factors is data availability. And I'd argue that probably the two fields which have shown the greatest progress in machine learning have been computer vision and NLP. And that's both because they've got huge publicly available data sets. So in computer vision, you have ImageNet, and in NLP, you have data sets like, well, the whole internet available. And it's training on these giant data sets, which has helped us develop some of these really amazing models because these models are really data hungry. But in medical imaging, we have some limitations with data sharing because obviously medical data is personal data and it's protected by law. And this means hospitals can't share huge data sets and make them publicly available and allow people to train different models on them. And this limits, in some ways, the development of machine learning models. And this is where generative AI can have a really big impact. So it has immense potential in creating large synthetic data sets, which kind of capture the important characteristics of real data sets, but without leaking any actually sensitive patient data. So you can imagine a hospital training a generative model on, I don't know, all of its brain MRIs from the last 20 years of its acquired, and then drawing lots of samples from that data set and sharing that synthetic data set without those worries about leaking anybody's private data. But that's not the only way generative AI can have an impact in medical imaging. So if you have a model which has modeled the underlying data distribution well enough that it can draw samples which reflect the underlying distribution, that also suggests that you have a model which in some way understands the underlying data. And that opens up kind of applications like anomaly detection, image-to-image translation, denoising in super resolution, and MRI reconstruction, to name just a few. And so, given the importance of generative models, their increasing importance in the field, we've been working with MONAI to develop an extension package called MONAI Generative Models. And the aim of MONAI Generative Models is to make it easy for researchers and developers to easily train, evaluate, and deploy generative models with an especial focus on medical data. So there's plenty of generative model packages out there online on GitHub, but none of them really target medical, or many of the popular ones don't target medical image data. So for example, Hugging Face Diffusers is an amazing package for training diffusion models, but I remember being very frustrated when I tried to train 3D diffusion models with it because that's just not really what it's designed for, and it had limited support for that. So we've invited a load of collaborators to work on MONAI Generative, and it's now released. The main features we've got are state-of-the-art models, with an initial focus on diffusion models and transformers, and I'm going to talk through examples for both of those. We plan to support a whole range of generative models, like, for example, our next milestone is to support GANs, but we've really focused on those two models for now, because probably they're the models which are being most used in the generative AI community at the moment. New losses and supporting classes to help train and sample from the models, evaluation metrics. We've really focused on trying to implement a large number of tutorials to cover both the models and applications of the models. So there's a whole bunch out there, which I encourage you to check out. And we also want to make available pre-trained models for people to download and use. And I'll talk about that a bit later on. So at the moment, MONAI Generative is a separate package within the MONAI Generative umbrella, and you can just pip install it right now. You can also log on, navigate to the generative models repo and start playing with it, raising issues, pull requests, and things like that. In the medium term, we're planning to port MONAI Generative into MONAI Core, but that shouldn't change much for you. It should just be that any imports you have will change from MONAI Generative.networks import diffusion model to from MONAI.networks import diffusion model. So the underlying experience shouldn't change, and it should be a very painless transition for users. So I just want to make sure we're all on the same page and discuss what is a generative model. So a generative model is a type of machine learning model designed to learn the underlying patterns and structure of a data set, and then be able to generate new data that is similar to the original. So if we imagine we have some underlying complex data distribution, this blue manifold here, and we have various points on that data distribution. So each point here is a brain MRI. Now, this data distribution is extremely complex and high dimensional, and we have no analytical function that describes that data distribution. So we need to estimate it somehow. And so we seek to build models which estimate that underlying data distribution as best we can using just data points from that data distribution and allow us to characterize and sample from that distribution. And it's no surprise that given the huge complexity of these distributions that neural networks have proved incredibly powerful tools for characterizing these data distributions. So I'm going to take you through two examples of these two models that we've kind of focused on supporting, diffusion models and transformers, and I'm going to walk through kind of a different application of diffusion models for each of these. So I'm first going to talk about image synthesis with diffusion models. So diffusion models, generative models which take a Gaussian noise input, and through a series of iterative gradual denoising steps, they can transform it into a sample. Here's an example of that here. And in practice, we have a forward process where we take noise-free data and we corrupt it gradually to up until xt here on the left here, which is a kind of a pure sample from a Gaussian distribution. And that's a fixed process which typically we control. We decide what that's going to be, how much noise is applied at each step. And then we learn a denoising process. We learn a model which learns how to produce x of t minus 1 given x of t. And generally, we use a UNet architecture as the backbone for our diffusion models. And we use the same architecture with the same parameters for each of the denoising steps. And we feed as additional conditioning information the time step that we're on to the network, so it knows kind of at which point it is on that denoising cycle. So getting a diffusion model in MONAI Generative is as simple as importing it like so. I spoke earlier about the difficulty sometimes in applying some of these generative models in 3D. So we have kind of native support for 3D or 2D models. So changing from 2D to 3D is as simple as just changing that spatial DIMS argument when you initialize your network. We also support noise schedulers. So these determine both how much noise is applied at each point in the forward noising process through the beta schedule. And we have a few standard schedules available for you to use out of the box, but we also make it very simple for you to define your own schedules if you want to experiment with the latest new schedules. And here we've implemented the standard DDPM scheduler, but we have other schedules available, which I'll talk you through later. And I mentioned we've got a bunch of tutorials available in MONAI Generative. So I'm going to briefly talk you through this 3D DDPM tutorial. The link to it is at the bottom here. I think these slides are going to be shared at the end, so you should be able to access these links. So I'll just talk you through some key parts of the tutorial. And in this tutorial, we're going to train a 3D DDPM on Bratz data. So we define the transforms, and the transforms are just pure MONAI transforms. Which means you have all the advantages of having MONAI's kind of ability to load different types of medical data, save different types of medical data. You have medical image specific transforms such as elastic 3D transforms, which are able to operate on both images and segmentations in parallel, things like that. So you define your transforms, and then we want to train on Bratz data, which is a subset of the decathlon data set. So MONAI, that's as simple as importing from MONAI.apps the decathlon data set and specifying we want task 1, which is the Bratz data. And I should point out here, we're training a relatively small DDPM, so we're downsampling in the transforms our data to about 40 cubed. So that just makes the tutorial faster to train, so it's quicker for you guys to get up and going with it. You don't have to wait 12 hours to train your model if you've just got a single GPU. But I'll talk later about how we can use the package to train higher, train DDPMs on kind of full resolution data as well. The training loop is kind of simple PyTorch. We define our pure noise, we randomly sample time steps, and we use our scheduler to add that noise to get our noisy images. I just realized I'm pointing my mouse, but you can't see my mouse. This is a bit better. And then we predict for noise using our model, and it's just a simple mean squared error loss. And then sampling images is also simple. We just loop over the time steps. So we set 1,000 inference steps to our DDPM, and we loop over them, iteratively get our model output, and then just step forwards with our scheduler to iteratively denoise our image until our image is a sample. So we start with pure noise and we end with a sample. And this is just an example of a sample we've drawn from this 3D DDPM tutorial. You can see the iterative denoising process here. And we've also tried to implement some helper classes, which makes it easier to do some of the common things, like some of the common training and sampling steps in generative models. So we have these inferrer classes. So here we have a diffusion inferrer class, which we just initialize with our scheduler. And sampling with that class is as simple as calling inferrer.sample and giving it upper noise, our model and the scheduler that we want. So this just means you don't have to write the for loop and iteratively apply your model and then step forward. It does that for you. Okay, so it just makes things, it's kind of a small quality of life improvement. The inferrer is also, if we just call forward on the inferrer, it gives us our noise prediction. So it simplifies some of the training steps. It's up to you if you use this or if you want to kind of have each of the step of the training loop written out step by step. These are entirely optional, but they just make the code a bit cleaner if you want to use them. And just to talk through some of the other features we have kind of supporting generative diffusion models, we've got different noise schedulers available. So we've got the DDIM scheduler, which aims to allow you to produce samples in fewer steps without loss of quality. So if we initialize this DDIM scheduler and we set the number of inference steps to 250 rather than the 1,000 it was trained on, we can get a sample in 55 seconds on a single GPU rather than 225 seconds from the DDPM. We also support other schedulers like the popular PNDM scheduler. Different parameterizations. Some example I showed, we have the epsilon parameterization where the model seeks to estimate the noise applied, but we can also choose to get the model to estimate the kind of clean sample at every step in the training process, or the prediction, which is kind of like a weighted combination of the two. And changing the prediction type is as simple as just specifying the type you want when you initialize your scheduler. And this is just an example of the training loop using the prediction. So we just use our scheduler to get the velocity that we want. Our model predicts the velocity, and then we just call our mean squared error loss on those two. One of the reasons diffusion models are so popular right now is that they're really powerful models for doing conditional sampling. It's really easy to condition them to produce kind of or control the image generation process. And we support the supplying of different contexts during training and sampling to our models. So a model with sampling is as simple as specifying with conditioning equals true when you initialize your model. And then when we call forward on our model, we just supply the conditioning as context there. So diffusion models are great, but one problem with them is they don't scale that well either to high resolution 2D data, and especially not to high resolution 3D data. And for that reason, we support latent diffusion models, which have a first stage sort of compression model, and then we train the diffusion model in a kind of a compressed latent space. And this is an example of a 3D latent diffusion model trained on the UK biobank data at native kind of full resolution. It was published by Walter Pinaya in MONAI workshop last year. And we support these first stage models in the latent diffusion models, so autoencoders and VQVAEs. So not only do we support the models, but we support some of the bits you need to help train high quality first stage models, so perceptual losses and adversarial components, so we can get really good reconstructions from these models, which hopefully encourages higher quality latent spaces, which is the space in which we train our generative models on. And I'll have an example of a pre-trained latent diffusion model later when I talk about the model zoo. And I want to talk a bit about transformer models. It's the other type of model we've worked really hard to support well in MONAI Generative. And I'm going to focus on the application of doing anomaly detection with transformer models. But of course, you can do image synthesis with transformer models. You can do anomaly detection with diffusion models. So these are just examples of one way you can apply each of these types of models. So when I talk about localized anomaly detection, I mean that at train time, we just have a load of clean, healthy images. And at test time, we want to take our model and give it a pathological image, and in an unsupervised way, get some sort of delineation of the pathology. And in particular, I'm going to be talking about anomaly detection with VQ-VAEs and transformers. So first, I'll briefly talk about what transformers are and why might we use them. So transformers work on sequence data, and they're most famous, I think, in NLP. So in NLP, we might give a transformer a sentence. So here, what is Project MONAI and when should I use it? And it will tokenize those words to convert them into kind of integers and arrange them as a one-dimensional sequence. And then we'll train a transformer to predict the probability of the next token given all previous tokens. So the probability of token SI given all previous tokens. And I guess the most famous example of transformers right now is ChatGPT. So I fed this question to ChatGPT, and it tokenized it, and it did next token prediction to kind of produce this really nice answer describing what Project MONAI is, which has kind of both long-range coherence and structure, as well as kind of like short-range details and good grammar and things like that, which just shows how powerful these transformers are. And of course, we're working with image data, and images aren't one-dimensional, they're two- or three-dimensional. So we need to do some sort of collapsing to get our two- or three-dimensional image into a one-dimensional sequence in order to train our transformers on them. And in particular, I'm going to be talking about decoding only transformers, which are transformers which only look back in time. They only look at previous tokens to make their decision of a next token. They don't look at tokens later on in the sequence as well. And so this is an example of defining a transformer in MONAI Generative. We save a number of tokens we have available. The max sequence length, which here is kind of the max size of our image, so the X dim times the Y dim, and some parameters for the attention layers. And we also provide this ordering class, which takes care of taking your 2 or 3D image and collapsing it to 1D, and also taking your 1D sequences and reshaping them to 2 or 3D for you. So we initialize that, and so you don't have to take care of any of that accounting for you. But I mentioned we're going to be working with VQ-VAEs plus transformers. So why not just apply transformers directly to image data? So they have an n-squared memory dependence on the sequence length n. So in a typical application in NLP, you might have n equals 1 to 3,000, 1 to 3,000 tokens context length. GPT-4 is capable of up to 32,000 tokens in its context and its memory. I think Claude, which is a new language model published by Anthropic, is capable of context lengths up to 100,000. If you take an 128 cubed image and you consider each voxel in that to be a token, that will have 2 million tokens, which is just far beyond the kind of sequence lengths we can reasonably train transformers on. So we'll only be able to take maximum 100,000 tokens into account. So your transformer won't be taking the full image into account when it makes its next token prediction. So you'll lose that kind of long range structure and coordination that makes transformers so powerful. So we introduced this vector quantized variational autoencoder, which takes our image and provides a really compact, discrete latent representation of that image, which we can then train our transformers on. So the compression rate of a 3D VQ-VAE is 2 to the 3L, where L is the number of layers in a VQ-VAE. So if we have a standard 4-layer VQ-VAE, we get a compression rate of about 4,000. So suddenly a 128 cubed image, its latent space will have a sequence length of 512, and that's easily able to fit into the memory, the context length of the transformer. So we can easily train transformers on the related spaces of even really high dimensional 3D medical imaging data. So this just kind of shows the whole pipeline. So you train your VQ-VAE to produce these representations. In practice, we often train VQ GANs. So we have some kind of adversarial component on the decoder to encourage them to produce the best reconstruction as possible. And we've got tutorials for how you train VQ GANs in MONAI Generative available. We unwrap our latent space to 1D, and then we train our transformer in the normal way on that 1D sequence. So we have VQ-VAE or architectures available, again, supporting both 2D and 3D data out the box. One of the tricky things about training these VQ-VAE transformers is you have to kind of do some accounting. Are you in latent space? Are you in image space? You have to kind of do transforms between latent space for training, but then when you want to see your images, you have to decode to get back to image space. So we have another inferrer, a VQV transformer inferrer, which you can provide your VQV model for, your transformer model for, your ordering class, and it does a lot of these transforms for you. So you can just call .sample and it will provide a sample for you, transform it into image space and things like that. So again, it just makes it's like a quality of life improvement for training some of these two-stage models. And so we've got a tutorial available for training a localized anomaly detection model with VQVs for transformers. Again, the link here is at the bottom. And we implement this quite simple method. So we train a transformer on the latent space of some data. And then we give it the sequence for a new kind of, imagine, pathological image. The transformer classifies the probability of every token in that image, and we threshold to highlight the low probability tokens, the tokens which the transformer says, given previous tokens, I think these tokens are very unlikely, which likely means they correspond to some sort of pathology, or hopefully that the transformer hasn't seen during training. And then we heal our sequence. So we say, okay, well, given these previous tokens, what is the most likely token we'd expect for this very unlikely token? And we replace that tokens, and we do that iteratively along the 1D sequence. And we take our healed sequence and we use our VQV decoder to transform that back into image space. And we have this reconstruction, which hopefully has the pathology removed. So in the tutorial, we take a clean image and we artificially corrupt it by adding this big white block. We get the likelihood of each token from our transformer. We threshold based on a probability value to get the mask. These are the tokens which we want to heal. So remember, our token is 1D, but I've reshaped them back into 2D to kind of overlay with the image, just so we can kind of see where these tokens spatially correspond to. And then we have some code in the tutorial, which just shows you how to heal this image. And here's the healed image here. So here's the image after healing and projecting back into image space. So I'll just flick back and show you the clean image, and you can see that the healed image looks fairly similar. It's had that pathology removed. And then we just do a simple image space subtraction to get a predicted anomaly mask. This is compared to the ground truth anomaly mask, so it's not too bad. We don't train the models for that long in the tutorials because we want you to be able to, within half an hour, get results. So these results could probably just be improved by just training both the VQV and the transformer for longer, but that's something that you're free to do if you want to. And I just want to talk about one last thing, which is the model zoo. So Stephen spoke about the model zoo, which you have available in MONAI Core, which has lots of different pre-trained models which are free to download and get using. We have a MONAI Generative model zoo, which currently lives in the MONAI Generative package. As part of a port to MONAI Core, it will be transitioned over to the MONAI Core MONAI zoo, but that will be in a few months' time. Currently, we've got two models. They're both latent diffusion models. One is for training brain MRIs from the UK Biobank, and one is for training chest X-rays from the MIMIC dataset. Here's an example of T1s from the Biobank, and some examples of chest X-rays. And I just really quickly want to show you a minute-long video, which shows you how easy it is to kind of use this model zoo to draw samples from these pre-trained models. So I'm going to show you a video for drawing samples from this T1 weighted brain model from the UK Biobanks. It's been trained on a huge, I think, tens of thousands, maybe hundreds of thousands of scans from the UK Biobank with conditioning for age, sex, ventricle size, and brain size, so you can control your samples. So I'm just on my computer here in the kind of MONAI Generative repo, and I've gone to the model zoos subfolder, and specifically to the brain image synthesis subfolder. And let's see if I can get this working. Just need to turn off my printer, I think. Yep, okay. So in the documentation, they just tells you the command that you need to run from within this folder to draw a sample. So here it is, I've just copied and pasted it, and you can see you specify gender, age, ventricular volume, and brain volume. And then I'm running through those 50 steps of a latent diffusion model to draw the sample, which takes about 6 seconds on just a kind of consumer grade NVIDIA GPU I've got on my machine. So that's one sample drawn, and we can just ls and see that it's available in the outputs folder. I'm going to draw one more sample, but I'm going to change the conditioning. So I'm going to reduce the age, or so increase the age to the maximum and decrease the ventricular volume to the minimum. So all these conditionings are normalized between 0 and 1, floats between 0 and 1. And that will draw another sample, which will take about 6 seconds. And while that's drawing, I just flick to my local machine and download them because my local machine doesn't have a GPU, but it does have an image viewer, and I just want to show you the samples. So once they're downloaded, I'll just open up the first image, the first sample I drew. We can flick through it here. And so this is a pure sample drawn from the latent diffusion model of a UK biobank. It's not a real image from a UK biobank. And you can see it's high resolution. It has kind of pretty good, it looks pretty good. And I'm just going to show you the other sample where I increase the age and reduce the ventricular volume in the conditioning. So this should have really small ventricles because it's an older person with small ventricles. And you can see that's true. So the conditioning has been respected during the sampling process. So you can just download these models from Model Zoo and produce potentially unlimited data sets with different characteristics by changing sex and ventricular volume and things like that, and train your own models on these large synthetic data sets, which I think is really cool. So on that note, I just want to say, thank you for your time. You can reach out to me by email, Twitter, or through issues on the MONAI Generative repo, and I'm happy to take any questions.